Now, we discussed in section 1.1 how we would eventually be coming back to the idea that that we can find the area under a curve using the area of rectangles and actually using that to approximate. So this is where we're going to take a look at that. So in geometry, the simplest type of plane region to find the area of is the rectangle, because the area is base times height. So basically, there's two different ways that you can do this. You can draw your rectangles under the curve, in which case you're missing a little bit of the area. These pink spots would be kind of an underestimate. Or you could draw your rectangles outside of the curve, in which you would overestimate your area. So there's two different ways that you can approach it. So let's take an example. We're going to use 5 rectangles of equal width to estimate 2 different approximations of the area of the region between the graph of f of x equals x squared plus 5 and the x-axis between 0 and 2. So basically, we are looking at between 0 and 2, we're looking at this kind of yellow region right here that I'm going to poorly shade in for you so that you can see kind of the shape that we're trying to find the actual area of. Okay, so this is what we're looking for. And if we wanted to do the 5 rectangles, you have 2 units of space. So if you take 2 units divided by 5 rectangles, that means that each rectangle will have a width of 2/5 units. Okay, so there's 2 different ways we can do this. So if I wanted to do the overestimate, if I take a look at this, I would want to draw the rectangles on the top. So basically, I know that I'm going to need to mark off kind of 2/5 for each rectangle. And basically, if I want to do the overestimate, I'm going to kind of look from the right, because this function is increasing. So that means this would be one rectangle. This would be another rectangle. This would be another rectangle. This would be another rectangle. And this would be the last one. So the height of each rectangle is going to be determined by the right endpoints of each rectangle. So in this case, x of 1 would be 2/5, x of 2 would be 4/5, x of 3 would be 6/5, x of 4 would be 8/5, and x of 5 would be 2. So basically, the height of each rectangle, the height is going to be f evaluated at whichever x of I I'm using, and the width is going to be 2/5. So the area of one rectangle is going to be equal to 2/5 times f of x of I, or 2/5 times x of I squared plus 5, because that's f of x of I. And the area of all of the rectangles would be the sum from I equals 1 to 5, since we have 5 rectangles, of 2/5 times f of x of I. So the sum from 1 to 5 of 2/5 f of x of I is going to be, I'm going to go ahead and bring the 2/5 out to make our work a little bit easier. And in this case, we're not actually plugging I strictly in, we're plugging I into the subscript. So this is going to be 2/5 times f of x of 1, which was 2/5, plus f of x of 2, which was 4/5, plus f of x of 3, which was 6/5, plus f of x of 4, x of 5, which was, 4 was 8/5, and then x of 5, which was 2. So this is 2/5 times 2/5 squared plus 5, plus 4/5 squared plus 5, plus 6/5 squared plus 5, plus 8/5 squared plus 5 plus 2 squared plus 5. And if you add all of that arithmetic together and multiply and everything, you get 338 over 25 units squared, or that actually is 13.52 units squared. Now if I want to come side by side and do the underestimate, I'm going to kind of draw off these same 2/5 unit intervals here. The underestimate would actually start from the left on this function. So that would be one rectangle. That would be the next. That would be the next. That would be the next. And that would be the next. So you can see the height is actually starting from x of 1 equals 0, x of 2 equals 2/5, x of 3 equals 4/5, x of 4 equals 6/5, and x of 5 equals 8/5. The 2 never gets to determine a rectangle here. So same exact formulas here, it's just we've got different x of i's. So for this side, the underestimate, we've got the sum from 1 to 5 of 2/5 times f of x of I, or 2/5 times the sum from 1 to 5 of f of x of I. But in this case, we're going to have different x of i's. So I would have the sum, or I would have, let's see, f of 0 plus f of 2/5 plus f of 4/5 plus f of 6/5 plus f of 8/5, which gives me 2/5 times 0 squared plus 5 plus 2/5 squared plus 5 plus 4/5 squared plus 5 plus 6/5 squared plus 5 plus 8/5 squared plus 5. And when you do all of that arithmetic, you get that that is 298 over 25 units squared. And this actually has a nice terminating decimal too, as 11.92 units squared. Now the reason why I went ahead and put this in decimal form is so that you can actually compare it. Okay, so this is saying that the actual area of the shape is between 11.92 units squared and 13.52 units squared. So it gives us a range for the area, but not the exact area. So what we've actually found here on the left is a lower sum for the area, and on the right is an upper sum. So if we want to generalize this idea of upper and lower sums, this is basically how we would do it. So if I've got a curve like this one, sometimes it's increasing, sometimes it's decreasing. We're going to divide it on the interval from A to B, that's what's shaded. We're going to divide that interval into subintervals of width delta x, which will always be b minus a divided by the number of rectangles we want. And to find the area bounded by the graph of the function x equals a, x equals b in the x-axis, we get that delta x. The endpoints of each rectangle or interval will be some x of 1 through x of n, and we're going to actually let x of 0 be a. Okay, so we let f of little m sub I be the minimum value of f of x in the ith subinterval, and we let f of capital M sub I be the maximum value of f of x in the ith subinterval. So if you're graphing this thing, you can see that for this rectangle, this would be the lowest point, this would be the little m sub I, and this would be the capital M sub I. But if you were looking at a different integral, or a different interval, let's say you were over here, that would actually swap places. So this one would give you the m sub I, and this one would give you the m sub I, the capital M sub I. It just depends on what direction the graph is going. Now we're going to call any rectangle that's lying inside the subregion an inscribed rectangle, and rectangles extending outside the region will be called the circumscribed rectangles. So for each I, the area of the inscribed rectangle, which is f of little m sub I times delta x, is going to be less than or equal to the area of the circumscribed rectangle, which is f of capital M sub I times delta x. And if you add up all the little m sub i's, you get a lowercase s of n, that's the lower sum. And if you add up all of the area of the capital M sub I rectangles, you get an upper sum, capital S of n. And the actual area must fall somewhere between these two values. So the area of the region is between little s of n and capital S of n. So you can see that here, the actual pink shaded region here, area will be between these two values. So we're going to find the upper and lower sums for the region bounded by f of x equals negative 4x plus 5, the x-axis, x equals 5 and x equals 1. So you can see that I have graphed this line. It's just a decreasing line, and the shape, because we're going from 0 to 1, it kind of makes a triangle with its nose chopped off, if you want to think of it that way. Notice it doesn't tell us the number of rectangles, and that's okay. We're just going to let that be general. So we're going to let n equal the number of rectangles. And for that n, our a here is 0, our b is 1. So the width, or the delta x, is going to be b minus a over n, which is 1 minus 0 over n, or just 1 over n. And since we know that f of x is decreasing, we can let m sub I, capital M sub I, be equal to the left endpoints. Now the cool thing about left endpoints, if you know it's always a left endpoints, there's actually a formula to find that. These are going to be a plus I minus 1 times delta x. This assures that we start at a. So in this case that would be 0 plus I minus 1 times 1 over n, or I minus 1 over n. And we're going to let our little m sub I be the right endpoints. And they have a formula as well. That's going to be a plus I delta x. So that would be 0 plus I times 1 over n, or I over n. Now when I go to find the lower sum, little s of n is going to be the sum from 1 to n of f of little m sub I times delta x. So that'll be the sum from 1 to n of f of I over n times 1 over n. So this is the sum from 1 to n. If we plug this I over n in, that would be negative 4 times I over n plus 5 times 1 over n. And if I bring in the constant here, this would be negative 4 over n squared times I plus 5 over n. And if I split this sum up and remove the constant, this would be negative 4 over n squared times the sum from 1 to n of I plus the sum from 1 to n of 5 over n. And if we apply the formula, we know the sum of I is n times n plus 1 over 2, and the sum of a constant is n. So from here, I just want to find a common denominator. I'm going to cancel an n here and a 2 here. But I'm not going to cancel this n because it'll give me the common denominator I want. So this will be negative 2n minus 2 over n. And this will be plus 5n over n. So this gives me 3n minus 2 over n. So that is my lower sum for any value of n. Now if we want to find the upper sum, it's going to be very similar, capital S of n. It's just going to be, instead of lowercase m sub I, we're going to use capital M sub I times delta x. So this will be the sum from 1 to n of f of I minus 1 over n times 1 over n, which is going to be the sum from 1 to n of, if we plug this in, negative 4 times I minus 1 over n plus 5 times 1 over n, which is going to be the sum from 1 to n of, we could have negative 4i, if you bring in the n, that'd be over n squared, plus 4 over n squared, plus 5 over n. Okay? And then from there, I could bring out the negative 4 over n squared and have that as the sum from 1 to n of I. And then there's no I in the rest of this expression, so this is actually just a constant. So this would be negative 4 over n squared times n plus 1 over 2 plus 4 over n squared plus 5 over n times n. Okay, so I'm going to cancel one of the n's here. I'm going to cancel the 2 here. So this will give me negative 2n minus 2 over n plus 4n over n squared plus 5n over n. And if I cancel one of the n's here, I can add all of that together, and that'll give me 3n plus 2 over n. So that would be my upper sum. So this tells me that for any positive integer n, the area of my shape is between 3n minus 2 over n and 3n plus 2 over n.